For the second part, we're looking again with the Lewis relationship. However, this time we're looking at it with the wet bulb and dry bulb temperatures as well as relative humidity. Now, to understand how those concepts go together, we're going to look at the wet bulb and dry bulb and relative humidity first. With wet bulbs, you have a liquid within the thermometer to measure temperature, and as that water evaporates, it actually reads a lower temperature than the ambient temperature is. Now with the dry bulb, without the evaporation, reads a approximate equaling of the ambient temperature, and then the difference between dry and wet will give you relative humidity. So we're going to look at the Lewis relationship we developed last time. I'm going to break it back down into its component of the mass diffusivity over the thermal diffusivity. Now the thermal diffusivity is actually the conductivity over the density times heat capacity. Density times heat capacity is also the volumetric heat capacity. Now if you put that back in, you get the term for your Lewis relationship to be the mass diffusivity times your volumetric heat capacity over conductivity. If you use that term with the wet bulb or moist air numbers, you get an approximate value of 1. Now, if we set that equal to our equation over here, we can actually simplify it to get the heat capacity by itself. So you have the mass diffusivity, or the mass transfer coefficient, or mass diffusivity coefficient divided by the conductivity equals 1 over the volumetric heat capacity. Now if we look at our Nusselt over our Sherwood number, we'll see some similar terms. And you'll see, using the secondary part that we can isolate our mass diffusivity constant over conductivity. So we have our heat transfer coefficient over our mass transfer coefficient, and then our mass diffusivity coefficient over conductivity, which gives us, using this, the heat transfer coefficient over the mass transfer coefficient is equal to the volumetric heat capacity. Now we're going to look at setting the heat and mass transfers equal to each other so we can figure out the relative humidity from our work. So we have the heat, which is the heat transfer, we're going to go mass transfer coefficient times the concentration of the surface minus the concentration of the environment. We're going to set that equal to the heat, which is the heat transfer coefficient times the temperature of the environment minus the temperature of the surface. Now, if you look at this and break it down by units, we have meters per second, and then we have moles per meter cubed, and we have Kelvin, and we have watts per meter Kelvin. Now, this this Kelvin cancels out, and we're left with watts per meter on the right side, and on the left side, you ended up with moles per meter squared per second. Now, to cancel out, we're going to have to use the heat of vaporization, which is joules per mole, to set the to make sure the units cancel out on both sides. Now, once given that, we're going to use our last relationship over here. The heat transfer over the mass transfer coefficient is equal to the volumetric heat capacity. So we're going to take the mass transfer coefficient and put it over there to give us this portion. So we end up with heat of vaporization times concentration surface times minus the concentration of the environment, which is equal to the volumetric heat capacity times the temperature of the environment minus the temperature of the surface. Now, after we simplified that, we're going to have to look into making the terms in pressure so we can determine relative humidity. So for concentration of the surface, we have the, I'll rewrite it over here. So heat of vaporization and then the concentration of the surface, which is the pressure of the water at the surface over the gas constant times the temperature at the surface minus the pressure of the water of the environment divided by our gas constant times the temperature of the environment equals, for density we have pressure total over the gas constant R times the temperature average times the temperature of the environment minus the temperature of the surface. Now, having each one have a different temperature at the bottom, it'll be hard to simplify, but since the difference between the environment and the surface temperature is going to be approximately the same, we can say that the temperature of the environment is approximately the temperature of the surface, which is approximately the average temperature. So now that each one can be made into average temperature, you can simplify the equation by removing the bottoms of all parts, since they are the gas constant R times the average temperature. So we have the heat of vaporization times the pressure of the water at the surface minus the pressure of the water of the environment equals the total pressure. I forgot to put in the heat capacity. So pressure total times the heat capacity times the temperature of the environment minus the temperature of the surface. Now we're going to compare that equation to the third part's equation using adiabatic temperatures.